Hello, everybody. Welcome to the Beam Summit Online extension. My name is Pedro Galvan. I will be your host for this mini online event that we'll have today. It's a pleasure to be with you. Um, the online extension for Beam Summit is basically what we wanted to do is give the opportunity for some speakers who weren't able to make the trip for Beam Summit to present their sessions. Um, and those sessions will also be published to the Apache Beam YouTube channel, but we wanted to show them um, synced simultaneously, just for you all to, in case you had any comments, any questions, things like that. Not all of our speakers will be able to join live, but we'll make sure to share your questions with them so that they can answer asynchronously in case you have any specific questions for speakers. The program of today is a couple of hours. You can see it here in the YouTube, in the channel description, or if you go to beamsummit.org, you'll see a link to the program, and there you can see the details of the talks. We have 4 talks today. We will start with our first talk. Let me actually open the program. Our first talk is integration of batch and streaming data processing with Apache Beam. That is presented by Yoichi Nagai. Yoichi is based in Japan, and it's past midnight right now in Japan, so he wasn't able to join live. But we have the recording of his talk. Thank you so much, Yoichi. And if you have any questions, we can reach out to him. Then afterwards, we have integrating LLMs and embedding models into Beam pipelines using langchain by Ganesh Sivakumar. Ganesh will be available live to present that live. And then we have a talk from Beam Summit from the in-person event that was let me 3 weeks ago. I'm sorry, I had to count. It was 3 weeks ago in New York City. We had the Beam Summit in-person event. That was great. And we have in that event, one of the talks was about what's coming for Beam, Apache Beam in 3.0, and what's the roadmap, what it looks like. That was presented by Danny McCormick and Kenneth Knowles. We have that recording from the in-person event, and we will be playing it here. And then we will wrap up with build seamless data ecosystems, real-world integrations with Apache Beam, Kafka, and Iceberg by Rajesh Vayyala. That talk was originally scheduled to be part of the in-person event in New York City, but Rajesh was actually he wasn't able to travel in the end. I believe he got sick and made his best to make the trip, but it wasn't working. So we'll be happy to present those 4 talks. Feel free to post comments, questions. We will be monitoring the chat, and if the speakers are not live to available to reply to the chat, we will make sure to forward your questions to them. So actually, let's get started with our first talk. As I mentioned, that's Yoichi Nagai, and he'll be presenting integration of batch and streaming data processing with Apache Beam.
Thank you for giving me the opportunity to speak today. I am a data engineer at Mercari. Mercari is a company that provides C2C online marketplace services based in Japan. In today's presentations, titled Integration of Batch and Streaming Data Processing with Apache Beam, I would like to introduce Mercari's publicly available OSS, Mercari Pipeline, and explain how data is processed at Mercari. Here is today's agenda. First, I will introduce Mercari pipeline. Next, I will introduce the use of pipelines of stateful processing in Mercari. Finally, I will introduce our efforts to execute stateful processing more robustly by offloading state to external data store. Here is an introduction to data processing at Mercari. At Mercari, various data pipelines are developed and maintained, including batch data integration from various databases to data warehouse and other databases. Near real-time campaign perform promotions and fraud detections also used. As middleware for data pipelines, we use Cloud Data Flow and Apache Flink on Kubernetes to develop the pipelines. Mercari adopts a microservice architecture. Therefore, various teams develop and maintain their own services. As a result, various teams develop and operate their respective services. Microservice teams may need to develop and operate data pipelines as required. However, not all application engineers are familiar with developing or operate data pipelines. At Mercari, Go is often used for server-side application development, so there are not so many engineers who are familiar with Java and Scala, which are commonly used for big data development. In addition, each microservice often has its own databases, requires the handling of multiple types of large databases. For these reasons, we developed Mercari Pipeline as a tool to easily execute data pipelines without writing code. Mercari Pipeline is a tool for defining and executing Apache Beam pipeline in YAML or JSON format. This tool is available as open source software on GitHub repository. Define and combine the 6 options on the left side to define the pipeline. As the observant may have noticed, this concept is very similar to Beam YAML. This is because Beam YAML did not yet exist when we started development. If Beam YAML had existed at that time, we might have considered using it. The content of the option, two things are almost the same as those in Beam YAML. In options, define pipeline option. In sources, define the sources of data to process it. In transforms, define the content to be processed using the result from sources and the other transforms as input. In things, define the destination where you want to save the data from transform and sources. Sources, transforms, and things have predefined built-in modules, and you specify the parameter for each module. Sources and things have familiar predefined modules such as storage, JRBC, BigQuery, and PubSub, and such on. Transforms define modules that handle data processes such as BeamSQL, aggregation, and select, and some modules are defined for processing external data such as Bigtable. I'd like to explain these transform modules in more detail from this point on. The system option in Mercari Pipeline provides flexible settings for runtime configuration other than pipeline options. In args, various variables that you want to replace at runtime can be specified in the config file. By embedding built-in function in template text, it is also possible to easily embed settings such as today's date and time. Context is an option used to derive multiple processes from a single pipeline definition. As will be explained later, multiple pipelines that share common parts such as feature generation in ML, train, and predict can be simply defined as a single pipeline definition. Imports is an option for merging and using pipeline definition written separately at runtime. This is convenient when you want to manage independent pipeline definition individually. This slide explains examples of using the system context option. As shown in the example on the left side of the slide, each module has a tags field. These tags can be used to specify the context to which the module belongs. The example on the left defines a machine learning pipeline. During training, data stored in BigQuery is batch loaded to generate features, which are then saved to another BigQuery table. During prediction, features are generated in real time from data retrieved by PubSub and streamed to another PubSub topic. The processing logic for generating feature is the same during both training and prediction. Defining the feature generation pipeline separately would make management complicated. In this example, the feature processing definition is small, but feature generation processing can be often be complex and voluminous. Therefore, we want to use context to enable switching between training and prediction using a single pipeline definition. For modules used in both training and prediction, specify both train and predict in tags. For other modules, specify train or predict as needed. When executing the pipeline, only modules with the tag specified in the system context will be enabled. In this example, we used a machine learning pipeline, but there are other use cases such as switching between scheduled regular execution and backfilling. Mercari pipeline also includes pipeline development support tools. The support tools server provides functions such as pipeline verification, local execution, and deployment to the cloud via API and browser UI. Although still under development, it will be compatible with MCP server, enabling users to build pipeline while interacting with the MCP host application. This slide shows an example of pipeline definition using the UI of server, a development support tool. In this example, server is deployed to Cloud Run. The pipeline definition is described on the left side of the screen. In this pipeline definition example, questions are specified in the create modules, and the OnyxGen modules outputs the answer to each question using local LLM. The local LLM models is converted to an Onyx file using Gemma 3, uploaded to GCS and mounted to the path specified in the model parameter. The button in the upper right corner of the screen is used to evaluate and execute the defined pipeline. The dry run button does not actually execute the pipeline, but perform pipeline validation. The run button actually executes the defined pipeline locally on the server. Since it is local execution, it cannot process large-scale data, but it can execute small-scale processing without any problems. Whether it is dry run or run, the output schema of each module step is displayed when it succeeds. The launch button actually deploys the defined pipeline as a data flow job. The deployment project and region can be set as an environment variable in Cloud Run. Now, let's talk about the stateful data pipelines. This slide shows an example of real-time campaign conditions at Mercari. Customers who register as new members and participate in the campaign within 24 hours will receive points when they list an item within 24 hours after participant. They will receive 1,000 points for their first listing and 100 points for each the next 4 listings. To verify these conditions, 3 user events must be tracked in real time: user registration, campaign registration, and listing. This is an example of using Beam SQL module to evaluate this condition. Let's explain the SQL content. In the first query of with calls with additional fields, we are extracting the fields such as timestamp for each type from the three types of events that have been combined into one using union for the subsequence processing. The next query, granted incentive, aggregates the three types of events for each customer and evaluates whether to grant incentives. To aggregate by customer, the group by cause specify user ID, but due to the trigger settings made earlier, aggregation is executed each time an event arrives. To evaluate the incentive grant conditions, the following aggregation results are specified as a filter in having calls. One, register for the campaign after signing up for membership. The campaign entry was made within 24 hours after registering as a member. The latest listing was made after entering the campaign, and the latest listing was made within 24 hours after registering as a member. This query evaluates whether the event is eligible for incentive allocation. The last query calculates the points to be awarded for events eligible for incentives. Whenever there is a listing that meets the incentive awards condition in granted incentive, we count the number of valid listings for each customer and award points according to the number. Beam SQL uses the aggregation processing result as a state for condition evaluation. Since the pipeline remained active through the campaign period, specify a global window and accumulate mode to retain the state. Specify a trigger to evaluate conditions for each event input. There are several issues within this approach of using Beam SQL to retain state as aggregation result. This is due to the fact that the order of event data is not retained when performing aggregation. Since the order is not retained, it becomes difficult to make order-dependent condition judgment. For example, it becomes difficult to determine whether a purchase was larger than the most recent purchase amount, or to make a judgment based on the total of the most recent three purchase amounts. Additionally, there is a possibility that the same processing result cannot be obtained using batch and streaming. Batch is used for pre-evaluation of real-time campaigns, such as simulation when and who become eligible based on past data. Unlike streaming, where processing generally arrives in the order of event time stamps, in batch, the order may vary widely. While setting trigger to watermark may yield correct final processing results, it is impossible to verify the process such as the timing of the determination. To resolve this issue, we can use the dofunc state API instead of aggregation. Normally, dofunc is a mechanism for processing input data in parallel individually. By using the state API, it becomes possible to update and retain the state each time input data is received. Additionally, state can be used independently for each specified key, such as user ID. In State API, various types of state are supported, but in cases such as this, ordered list state is useful. This is a type of state that can efficiently manage order based on the event time of the input data. Furthermore, by using the required time-sorted input annotation, it is possible to specify the input in order of event time in batches. This makes it possible to combine the processing result of batching and streaming. It is important to note that the state API cannot distribute processing as much as combine function. So if the data associated with the key is large, the processing load may become uneven and memory usage may increase. And using the state API with Dataflow Runner version 2 is not recommended due to performance issue. This is an actual code example of do function using the state API. In addition to the input data, it is specified to receive two states. One state is that retains the historical input data that is needed. The other is a state that retains the historical data up to a certain point in time that is needed. It is used to delete historical states that are no longer needed. Ordered list state enable data retrieval by specifying a time range. Here, we specify the oldest past time inferred from the processing content and the current event time. We use this past data to execute stateful processing. After that, we delete all data that is no longer needed from ordered list state and add new data. Mercari pipeline provides stateful processing using this do function in select module. In the select parameter of the select module, you can specify the field name of the processing result, the processing function, and the range of past data to refer as a range parameter. If range parameter is not specified, processing will be performed on a per row basis as a user. The range parameter can be specified as either a number or a time span. The middle example calculates the sum of the result of the formula specifies the expression parameter for the most recent starting date point. In the next example of the lag function, range parameter is omitted, but calculations are performed by referencing past data with index. In this way, we can define processing such as window function. The following examples show how to perform time series prediction using stateful processing. Here, Kronos board, which is a foundation model for time series prediction, is converted to an Onyx file for use. Onyx is a machine learning model format that enables prediction processing built with Python to be executed in a runtime environment using other languages such as Java. This model predicts the next 64 points of data with a range of 9 quantiles based on the previous 64 points of data. Therefore, as input for this model, we use the array-arg function of the select module to create an array of data for most recent 64 points of the specified field value. The following Onyx modules input the array data into the Onyx model and output the prediction results. The mapping between the model input names and output names is also specified. In addition, since the prediction result of the model are outputted in 9 quantiles, specify the required range and quantiles as appropriate in the post-processing select. Here, the central prediction of result at the next point time are output as the field name forecast for 1. By applying the trained model using the Onyx module in this way, it is possible to run future generation and prediction on the same pipeline. So far, we have introduced an approach that retains state in pipeline processes. However, there are several issues with retaining state in the pipeline processes. In some use cases, it is necessary to retain state for long periods of time. Some campaigns may run for several months. Running for a long period of time also increases the risk of failure in pipeline. If a failure occurs, restoring the process requires recreating the state correctly. However, restoring a large amount of state is extremely difficult. Saving state snapshot also incurs costs. Additionally, modifying the content of state processing requires recreating the state from scratch. This increases the cost of change and makes modification more difficult. Therefore, instead of retaining state within the pipeline processes, we will explain an approach that utilizes the data required for state calculation by storing it on an external data store. This slide explains the architecture for offloading state to external data store. We assume that user events are published from each microservice to a PubSub topic. We also assume that historical data for building state is stored in Bigtable. The data flow pipeline for logging writes user events received from PubSub to Bigtable. CDC data is generated from the written by Bigtable. The data flow pipeline for processing receives CDC and execute queries on Bigtable. Stateful processing is performed on the event historical data from the query result, and results are published to PubSub for integration. The data flow pipeline for processing executes query via CDC because it may utilize various user events. This is because the pipeline for logging is expected to be deployed as a separate pipeline since it receives events from each microservices. This slide explains the process of recreating a state from data in external data sources. When user events are written to Cloud Bigtable, CDC data is generated from Bigtable based on the written content. From this CDC data, a query is generated to fetch the data required for stateful processing. In this example, we retrieve user behavior history in time series. So the query is generated using the user ID and update timestamp from the CDC data. Cloud Bigtable supports SQL, so we embed the CDC data value in SQL format. Since executing query on Bigtable for each CDC data result in high load, we keep the query result in memory. Only data newer than the previous executed timestamp is retrieved and merged. Stateful processing is executed using the retrieved query results. This is an example of the config settings. The Bigtable module of transform is used for stateful processing. Use query parameter to define query retrieved from Bigtable for use in stateful processing. Embed CDC data parameter is in the query. In reality, CDC data is difficult to use in its original format, so we format it into a more usable form before embedding it in Bigtable. But we have omitted this explanation for purpose of this presentation. After that, the stateful processing is defined with the selected parameter in the same way as the select module explained earlier. Instead of returning state in the processes, retrieving history from an external data store and executing stateful processing simplify the internal state of the pipeline and make it easier to operate. On the other hand, retrieving historical history and reconstructing straight each time increasing overhead. We are currently considering a mechanism that produces the same result for both batch and streaming. We are currently working on enhancing stateful processing using external data sources, but basically it's necessary to use different mechanisms depending on the requirements. Here is a summary of today's presentation. We introduced Mercari pipeline, a tool for defining and executing pipeline processing in YAML or JSON. Using content makes it easier to manage the definition on delivery pipeline. We introduced example of using aggregation and do function state API as a method for performing stateful processing with Apache Beam. We also introduced an approach that offloads state retention to an external data store instead of the pipeline processes. Mercari pipeline is still under development as OSS. Some of the features introduced today have not yet been included in the OSS version, but we plan to introduce them in a near future. We would like to share other interesting features that we were unable to cover today, such as an Onyx integration, at another opportunity. If you have any question or request, please feel free to contact us via the repository or social media. Of course, contributions are also welcome. Thank you very much for listening today.
There we go. I was muted. Thank you so much, Joshi. Um, and we are about, I mean, I just posted in the chat the email from Joichi in case you want to reach to him. Uh, on the video he recorded, the webcam, his webcam was on top of his email address, but he accepted to share that. So I just posted it on the chat. Or if you have any questions for him, feel free to post them or feel free to discuss with other people who are watching. Usually there's good conversations. You can find somebody else interested in the same topic. So feel free to use the chat for making questions and even to comment with other people who are watching, to discuss with other people who are watching. Okay, so next up we have our next talk. Our next talk is by Ganesh Sivakumar. Ganesh is here with us. He's live with us. Hi, Ganesh. How are you? Let me add you to the stage. There we go.
Hi, Pedro. I'm good. How are you?
Pretty good. So you are in. I, I now that I have you here, I've always wondered what is the correct pronunciation of, because I understand you're in Bangalore, but I don't know if it's Bengaluru or Bangalore or what is the correct pronunciation.
It is Bengaluru.
Bengaluru. Okay, okay. I think I kind of got it. Thank you so much for joining. We know it's late night for you. Thank you for being here. I understand you're going to talk about integrating LLMs and embedding models into Beam pipelines using langchain. So the floor is
Right.
yours. Let us will be sharing your screen, and everybody feel free to post any questions or comments in the YouTube chat. Okay, can we show Ganesh's screen? I believe that it is, oh, we have infinite mirror. So I guess there we go with the slides. Okay, floor is yours, Ganesh.
Yeah, awesome. Hi, everyone. My name is Ganesh, and I'm a software engineer. And in this session, I'll be talking about how to integrate LLMs and embedding models into Beam pipelines using LangChain. So the agenda for this session would be to I'll start with giving an overview about what B transform is and how B pipelines would be executed in general. And then I'll introduce langchain Beam library and its transforms, and then how to use the transforms in the pipeline, and then um, in the session with a demo of the pipeline. Yeah, to start with, P transform is basically a stage in the pipeline. It takes in the data and then applies the transformation logic on it, and then outputs the transform data. Um, there are multiple kinds of transforms, and you could create your own custom transforms. Uh, when the transform is applied on the input data, it basically outputs the uh, transform data's new set of P corrections. Uh, Now we'll talk about how Beam pipeline uh, general works. Um, picture this. Picture it as a river flowing through a forest. It can go through multiple splits and turns, and there might it might even uh, split it into a separate channel. Beam pipeline is just like that. The data source can be a waterfall. The waterfall is like a data source in a pipeline, and when the data reaches the transform, the transformation logic is applied on it, and then the new set of P collections elements is emitted, and then it reaches the next transform. Um, yeah, and there is bounded and uh, uh, bounded and unbounded peak collections. Data sources, just like uh, stream can flow continuously. The data will uh, flow continuously in unbounded sources. Um, so now I will introduce langchain Beam library. Um, Basically, it is an open source library that provides transforms for integrating models into the Beam pipeline. First transform is an LLM transform. Um, the uh, the transform provides abstractions to integrate various models and models providers like OpenAI and Anthropic into the transform and leverage the model for processing the data. Typically, a transform would have a predefined processing logic. Uh, with this landing transform, it processes the data using LLM based on a pipeline author provided prompt. Uh, uh, so it takes an input P collection of elements, and then uh, the transform uses the model to process the data and then outputs the langbeam output P collection, which wraps the model's output and the input element that was processed. So now we got an introduction. I'll talk about how to utilize this transform in the pipeline. Um, yeah, let's have a scenario, right? Let's think I have a product and I have some user feedback of my product, and I would want to extract. Basically, I might have tons of user feedback, and I want to understand what users would think about my product. And first step would be to define the instruction prompt. Basically, to tell what to do, to tell the model what to do with my data in the pipeline. Second step would be to define the model options. Model options is basically to define which model should I be. I'm planning to use, and then the API keys for authentication and other optional parameters like temperature to control the randomness. Um, there are multiple model options classes present in the library. Let's say if you want to use Anthropic model provider, you could use Anthropic model options class. And third step would be to define the handler. The handler is just an object that holds the options and the prompt, and then now we could use the transform in the pipeline. This is basic syntax that tells like first step would be to read the input data, and then second step applies the LLM transform, and then third step can be anything. The transform data can be input to a different next transform, or you could I could write it to uh, a data sync. Uh, Now that we know how to use the transform, I'll talk about uh, how the transform works internally. So just like any other transform, line transform has layers to it as well. The top layer, which is public, uh, as a exposes a run method and takes an handler. Um, and internally, it calls an do fund to basically inference with the model using the langchain Java. So now the Dufan would do a few things to for us to give us the output. First step would be to initialize the setup, initialize the I mean, connect to the remote models API using the LangChain's chat language model. Uh, right, and and it would perform chat language model is basically chat language model is part of LangChain Java. It is an base class for uh, interacting with various model providers. It provides methods for calling the model, and then it handles all the inference logic. And we would utilize this chat language model object in the process element to call the model. So as a first thing, for every single input element, a final prompt would be constructed where the input data and then the formatted output format would be injected into the prompt, and the model would be invoked, and then the model's output would be wrapped into this lang beam output and then emitted as a P collection. So this is the prompt template that I talked about in last slide. Uh, Basically, it provides context to the model, and during runtime, the placeholders would be replaced with the input element and the instruction prompt that pipeline author has provided, and the output format about the how the what's the model should respond it. Um, let's say let's go back to my previous example. I wanted to extract the sentiment and understand what my users would think about my product. Uh, this is a very basic example, and uh, the model is going to respond in a plain text. But let's say, what if I had to like uh, categorize the positive reviews and negative reviews, and then uh, use the add attach metadata to negative reviews, and then maybe reach out to the users and then get their feedback. Um, um, uh, to address that, you could provide the output format to describe what's the structure that model should respond into. For in my example, I want JSON structure of review, the products review, and then the sentiment, which the sentiment of the review. So now when I read data from my locally and then apply the LLM transform, I would get the output in a JSON structure, and further I could uh, group by the negative or positive reviews for further downstream processing. Second transform is embedding transform. This is similar to the LLM transform, same APIs. But it basically integrates embedding models into the transform, and it takes an input P collection of elements, and then uh, uh, generates vector embeddings for those elements, and emits the uh, vector embeddings plus the input element. Um, This is an example embedding generation pipeline. Um, First step would be to define the model options, and here I'm using uh, OpenAI's model, and uh, and I'm going to use the same previous data. I mean, my product will use data and then generate vector embeddings for it using embedding transform. Um, and then I might write it to a vector database or perform similarity search later on. Yeah, I would like to share a pipeline demo of the pipeline. All right, this is my like sentiment generation pipeline. I've defined the prompt and then I have my keys for authentication and then defined the my options and output format and I am loading the product reviews data and then applying the LLM transform. So I'll run the pipeline. And yeah, here I'm basically extracting the uh, model's output from the embeddings of the object, and the model has responded in expected JSON structure. And yeah, that's it. I would like to take if there are any questions.
Hi, Ganesh. Thanks so much for the talk. We have the, when you get a chance, please send us also your slides so we can share them with participants when we publish the talk. Let me see. Your talk was quick and we don't have any questions so far, but actually a question just came in. Azulan asks, did you experience a slowdown in processing in data flow job while making calls to the OpenAI models? I don't know if, let me read that again. Did you experience a slowdown in processing in the data flow job while making calls to the OpenAI models?
Okay, yeah. Uh, the calls based on uh, the inference part is handled by langchain, and uh, there can be default latencies for while calling the model. Uh, but yeah, latencies would be definitely be there. Yeah, because we would be making API calls. Yes.
Okay. We also have a question by Alexander Fragotses. He asks if you know if it's possible to batch calls together in order to lower costs, in order to save money.
Right. That's actually a good point. Currently, since the library is using LangChain, LangChain makes individual calls every for every single element. It makes an individual call, but OpenAI itself has an batch API that maybe we could replace LangChain part with OpenAI's batch. Direct OpenAI's client and then utilize the batching part.
Okay. Asulan just added to his previous question about the slowdown in the data flow job. He mentions that he has a streaming data flow job that uses run inference transform with Vertex AI model handler, and he experiences a slowdown in the data flow with no evidence of throttling or Vertex being the limit. So I guess Sulan, we'll make sure to share your question or your comment with a team in at Beam and Dataflow uh, to see if they have any insight on why that could happen. We also welcome you to send that, to post that question or concern to the mailing list, the developers or users. Actually, that would be for the users mailing list in Apache Beam. We will post the email address for that in the chat in a bit. But yeah, I think that would be a good question for the users mailing list of Apache Beam. Otherwise, I mean, Ganesh, I don't know if you have any comment about that. If not, we can forward that to the users mailing list.
Awesome. Yeah. Uh, run inference with Vertex AI might use basically perform remote inference, and remote inference could obviously have latencies. Right? Uh, might not be avoided, can't be avoided completely.
Okay. We have another question from Habs. Can you tell more about chunking recommendation for embedding large amounts of text? Is there some recommended approach?
It depends on the data that you would want to chunk and generate embeddings. There are you could do the straightforward uh, character chunking, which would chunk by a fixed number of characters, or you could use semantic chunking if you would want to chunk based on meaning and then generate embeddings. Just depends on the data and what you want to use it.
Okay. Well, I think that's it. Thank you so much, Ganesh. Thank you. We know it's late for you. Thank you for joining and doing this. When you get a chance, please also share your slides with us so that we can publish them, and we will add the session to the Apache Beam YouTube channel and the Beam Summit website.
Yeah.
Thank you.
Sure, Rajesh. Yeah, thanks.
And for the rest of us, we'll continue with the program. We have 2 more talks today. Next up, we have the Beam 3.0 and beyond, the future of Beam. That's a roadmap talk that was originally presented in New York City in the in-person event that we had in July 8 and 9 in New York City. So let me check. We are about 5 minutes ahead of schedule. Let's just wait a couple of minutes just so that people that uh, made a reminder to join to watch this talk, just so that we can wait a bit for them. So we're actually at this moment about 6 minutes ahead of schedule. Let's wait for another 3 minutes. In the meantime, feel free to go take some water or reply those pending emails, whatever else you want to do. We're going to put a video loop for about 3 minutes, and then we will restart with the next talk. Okay, see you in a bit. Okay, welcome back to Beam Summit Online Extension. We are now about to start the next talk, 3.0 and beyond, the future of Beam, presented by Danny McCormick and Kenneth Knowles. As you will see, that's a recording from the in-person event. We're seeing if Danny and or Kenneth or somebody from their team can join the chat. So feel free to make any questions, comments, discussion, and we'll make sure that those comments reach Danny and Kenneth. So let's get started.
I'm Danny. I'm a PMC member on Beam, and Ken, you want to go ahead?
Yeah, I'm Ken. I'm the PMC chair of Beam. There we go.
And today, yeah, we're talking about Beam 3.0 and beyond, so kind of predicting a possible future for Beam.
Yeah, I guess I'm starting. Okay, we'll pass this thing back and forth. Now I see it has arrows on it. That's how it works. Okay, so I'm just gonna first start off by saying that like Beam's code base now is like 10 years old. I've kind of been working on it most of that time. And the core is stable, it's mature, it's been proven in all sorts of contexts. And my thesis, and we can all have our own theses, but mine is that we've sort of entered an era of more building on top of the core than sort of continuing to fiddle with it. Although we're still doing a few things. So I'm gonna really quickly run through what I mean by that, just to sort of set the context to make the rest of what we say make sense. So these are the things that are stable and underlie Beam, and not just Beam, but most big data processing shares most of the same foundations. So start with Beam is the successor to MapReduce, or it's a descendant of MapReduce, right? That's where we sort of applied functional programming, and it inspired the entire generation of big data systems after it. Google researchers continue to work on this, and with Flume Java, they improved on that by figuring out that you could have a whole graph of maps and reduces, and you could optimize it so that you're, say, this is my attempt to illustrate fusing a bunch of maps together. So you run it on one box and doing things like combiner lifting to minimize how much data is shuffled. Now pretty much every system out there does the same thing, right? So this is a foundational approach to big data. Beam didn't just optimize existing primitives. Beam sort of worked on introducing new ones when you realize that we actually need like a little bit more expressivity. So this is like the diagram we use to talk about per key stateful workflows. And this has been mimicked in Flink, and I've seen it in a couple other little mini languages that people make. So this, regardless of how the diagram looks, is sort of like a fundamental primitive that is all over the place now. Something we don't talk about enough is Beam's dynamic splitting and work stealing, which is still awesome. And so what we have here on the left is sort of a diagram of like your typical like you split the data and then you process it. And this is like what a lot of people do, what the original MapReduce did. And I mean, God forbid your data is just pre-partitioned and you can't split it. But like if you have Beam's dynamic splitting can be a little difficult to use, but you end up with the diagram on the right, where you can steal the work, you can redistribute it, and you get much better runtimes. So Beam, obviously, we advocate that batch and streaming should be unified. You kind of, if you're running a streaming application, you need to be able to do backfill when you have a bug. You need to run experiments. And if you're running a batch application, and you want to have greater control over sort of the trade-off between latency, you want to be using the same code for both. And this is really just like a necessary aspect of stream processing. In streaming, we talk a lot about how event time and processing time, they need to be made independent. And when Beam sort of laid this out and this advocacy, right, this is just sort of generally accepted now. You can't really have correct time series processing if you don't treat the timestamps on your time series as derived from the data, as opposed to just like when you happen to be processing them. We incorporated this into SQL. We worked with people from Flink and Calcite and Oak Ridge National Lab, and we published a paper about sort of how we thought this could fit into standard SQL. It'll probably end up being a little bit different in the standard if and when that comes about, but the concepts are more or less going to be the same. It's just sort of a way of expressing how you can do aggregations over infinite data sets that have timestamps on them and still have a meaningful result. Oh my gosh, my slide got crazy. Okay, pretend this is the any language on every runner slide. This is that's exciting. But so what I'm gonna say about this, anyhow, I wasn't gonna say much about it anyhow, except to say that at this point, we have this protocol where we can take Go, we can take Python, we can take Java, SQL, we can take any language can sort of be expressed and then run on any data processing engine. And engines come and go, and they all have new ideas about how you do scaling, checkpointing, and scheduling. But what is stable as part of Beam that at this point is sort of proven that it's good enough and it really does the job is our protocols for calling your sort of business logic code from the runner, right? We know that it's stable and high performance. Oh, it's animated. I didn't even know this was animated. Okay, there we go. That's the picture we wanted. But anyhow, the sort of the proof is here. It's all of you here and all these logo slide, which is just to say that Beam is already used in a million contexts, right? So that's sort of the last thing I want to say about how the foundation is robust and the innovation is just now out there and we can rely on it. And then pass it to Danny.
So now I'm going to talk about kind of some of the challenges in front of us. So to Ken's point, I think we've built a really solid foundation here. But there are still kind of continuous challenges that come up and people ask about. And I'm going to focus on 3. So the first one is basically, how do I even write my data processing? We want to figure out ways to kind of lower the bar for this. It can be challenging for people who don't have a background in code or who don't have a background with Beam specifically to get started. The second thing here is, once I've written this, how do I maintain this? Obviously, we all know that writing the code is not the entire journey. It's just kind of a small part at the start. And it can be challenging to do things like manage my dependencies, update my pipeline over time. And Beam has primitives built in for this, but I think there's room to grow here. And then the last question is kind of the question that everybody has in this moment, which is, how do I AI, ML, LLM, insert buzzword here? How do I take kind of this really transformative set of technology and incorporate it into what I'm doing in my pipelines? So that brings us to Beam 3.0 and kind of, again, one possible vision for our future here with Beam. And this is based off of some of these questions we've seen and generally the kind of broader sentiment around the community. So I'll hand it back to Ken for the first pillar here.
All right. Okay, so yeah, pillar number 1 is to address this problem of like, how do you write your data processing, right? And throughout Beam's history, we've sort of focused on making it easier to use the thing that we've already got and just sort of incremental improvements. But I think going forward, and we're already moving into this phase, like pillar number 1 is access for everybody, right? We have not just programmers, not just distributed system experts. Just make it easier for everybody to author data processing pipelines. So first step that is you have to have access to your data. For most of Beam's history, there's sort of been this focus on really high performance, high scale, I would say like scale proof connectors for other systems that are intended for big data uses. And that'll continue, right? And right now, like Kamal mentioned, like Iceberg is super hot. Our Iceberg connector is developing really rapidly. You may have seen a talk on that at this summit. And another one that is still continuously improving, even though it's like fairly mature, is our Kafka connector. Like these are both like huge technologies. But a future direction is also to increase the number of IOs, right? Like this is my logo slide for connectors, and there's probably a couple more, but there's not like 500. But there should be really, because there's a million little systems that they're not ready for like data flow to hammer it with requests. That'll just knock over the storage system. But we do need to get that data out of there. And so to make that easier, just sort of building easy ways to just connect to an arbitrary data source. And so like request response IO, you may have seen a talk about how you can use that to make an IO quicker for like a sort of a simpler IO for a lower scale system, especially. Another thing that has sort of been a hallmark of Beam's history is that we shipped complex IOs as like, we would build these things and we didn't expect users to be able to write them. Like we'd write this transform, but then after that, everything else was like your logic. Like you figure out how to use Beam's primitives to like do your thing. But I think at this point, like instead of that, like there's this move towards what we've been calling turnkey transforms, especially pioneered in like the ML space with ML transform and run inference, where in the same way that IOs package up a ton of complexity and best practices, now we have these transforms that address specific use cases and verticals that are sort of prepackaged. You just configure them, and then you're able to get the job done. And so instead of being like we teach you the primitives and now you have a new way of expressing yourself, we just like give you the solution, and as long as you can express it in the language that makes sense for your business case, you can do it. Another thing that's like really democratizing is Beam YAML, and I think it exists and there's like a lot of space to grow here, but here I've drawn sort of the learning curve for Beam, which is that if someone else has written a pipeline, you can invoke it, and we kind of have systems of templates where you provide the parameters, and then you can do it, right? And that's very low barrier to entry. But then if you want something else, you kind of have to like learn to program, learn Beam. I mean, I assume not everybody wants to do that, and even if you like are an experienced programmer, it's not easy to use Beam. Not always. I shouldn't say that here. No, but right. So Beam YAML is trying to sort of like make the learning curve a little bit gentler, right? It both makes it so that there's some accessibility. You don't have, even if you're a programmer, you don't like have to set up a programming environment that's appropriate for your pipeline, so it makes it easier to get started. If somebody else has written sort of a Beam YAML pipeline, it's much easier to take it and modify it. So in addition to Beam YAML that exists today, I see in the future of Beam like a bunch of sort of expanding what it can use, because I think a lot of there's more and more transforms to be made into turnkey transforms that can be really easily inserted into a Beam YAML pipeline. And then there's tools built on top of it, right? Like Dataflow has this job builder tool that's a graphical editor for your pipeline, and you can sort of load Beam YAML pipelines into it, and you can save them. And in some ways, it's a Beam YAML editor, but also a graphical editor. And so it's like this perfect interplay of different easier to use tools for authoring your data processing. Okay, this is another aspect of like Beam historically, and it comes from this place, and there have actually been multiple talks at this summit that actually need the origins of like, you control serialization because that's a huge part of your cost, and so you want to like really minimize the amount of data you serialize. But this view that all the data flowing through your pipeline is custom serialized bytes, and like you are highly optimized for that, and it's your own custom sort of way of thinking about your data. It's kind of premature optimization in my view for a lot, and in terms of like making it more accessible for everybody, most data is actually structured. Like, even though you think of like, well, once it's structured, maybe I do SQL. I don't really think that's true. I think it's that like you can, but in general, like, data is structured. Sometimes that structure is too much overhead and you want to go back to basics and be like, I'm going to encode it my own way. But not generally. And so a big sort of thing that makes Beam more accessible is a move towards like making transforms that just consume and produce structured data. It's easier to debug. They plug together more easily. It unlocks SQL. Let's see, I had some other, yeah, it also sort of opens up opportunities for optimization and taking advantage of new technologies like Arrow when they come along. And the last one related to that, I'll actually be really quick about this, but it's like a more like new direction, which is to say like once you have structured data, the truth is a lot of what people are doing with Beam is just like shipping change logs from like one database to another. There's like a bunch of that happening. And we were mostly created with like sort of an insert-only view, which makes it so that the moment you actually need to do processing on these changelog records, you are back to not being able to use all the stuff that's already built into Beam. You kind of have to like manage it yourself, because even if your data has a column that says it's an insert or an update or a delete, like none of the stuff that's built into Beam actually understands that and does the right thing. So embedding CDC into the Beam model, and this is where I get bad contradicting my earlier statement, which is like, there is a missing piece of the model here, which is making CDC sort of persistent throughout the whole Beam model, so that when you're shipping stuff from your transactional database into your lakehouse, like all the existing Beam transforms just work. Like, I think that's an important future direction for Beam. Okay, so that's what I have to say about the first pillar. The second issue of, I'm also talking about this one, and then Danny's going to take for the third one, how to maintain a production pipeline. And I struggled for a name for this. We had like Easy Ops and Just Works. I hate Just Works as a name, but that's kind of, there's a couple different aspects to it, so I didn't have a good name for it. But operating your pipeline sort of has like two major sub-pillars, which is that there's the basic thing of just like, you've got to be able to get the metrics, and it should be as smooth and as few hiccups as possible. But then another aspect of it needs to fit into like what infrastructure you already have, right? And that's sort of like your Beam being placed into the context of your infrastructure. And I'll talk about a few things that are happening now, and there are presentations at this summit, and also are going to be moving into the future. So managed transforms is a big one. I hope everybody saw that talk. I love managed transforms. So this is sort of, if you're a user, you might think of your pipeline this way. You're like, I'm reading some stuff, do a couple do funds, do group by key, a couple more do funds, right? This is like, nobody actually writes pipelines this simple, right? But when you have a pipeline like that and you deploy it, you think, okay, I got the reading and the do fund, this is all the Beam code that I've written, that's kind of my problem. The runner's gonna manage like the metrics and the scheduling and the scaling, checkpointing, and that's the runner's problem, right? With managed transforms, sort of the thesis is that actually like the reading and the writing is just like, these are these super complex IOs that are built into Beam. And what managed transforms does is it makes it so that the runner can identify them in your pipeline and sort of take ownership of them to move to a world that looks more like this. So you've written the same pipeline, but when you deploy it, you think, okay, the runner's gonna take care of like reading the data, shuffling it, like all I'm thinking about is my do funds. My business logic is the only thing I have to get right. And so like, let's say there's a bug in the Iceberg library and you need, you want to upgrade your Iceberg library, but you're like, oh, I don't really want to upgrade the version of Beam because I'm like 16 versions of Beam behind because it's stable, right? Managed transforms, part of the idea is that the runner has the ability to say like, you're reading from Iceberg, I'm going to manage that. I'm going to like be like automatically upgrading you so that you're actually using the latest version of Iceberg IO and the latest version of the Iceberg library to do that read. Well, it's just not the user's problem anymore. So another aspect of when you're like sort of iterating on your local pipeline here is being able to do your local testing, experimentation and debugging in sort of a more manageable environment and having confidence that when you do deploy it, it's going to work in the way you expect. Now, Beam developed organically where we had like a Java runner and then we had a Python runner. Then we had another Python runner that was sort of able to do some of Beam's like cross-language capability. And it's been a challenge to have a local experience that was really easy to use and reliably represented what was gonna happen on deployment. So for very complex use cases, you have to sort of do some of your testing on Cloud Dataflow, for example. And you don't really know like for sure that how it's gonna work until you've done that. And so the Prism runner is kind of our answer to that. And going forward, we really will continue to be developing this, I think, because the purpose here is that like if you're just working in Python, you don't actually need the complexity of like a separate runner that was like, it's written in Go. You don't have to know that. But like running your Python unit tests on your sort of Python do funds, you still use the existing Python direct runner. But the moment it becomes more complex where you're like using a Java IO in your Python pipeline, which is totally an ordinary thing to do and like not even necessarily remarkable in Beam, you need something that will reliably represent what's gonna happen when you deploy that pipeline. So that's what the Prism runner is for. And I think there's a lot of like further development to go there to make sure that that really is a high fidelity representation of what will happen on deployment. And the very last thing I'm going to talk about, and this is more of an example, there was also talk on this from Stephen, this is sort of the Beam in context notion. This is like when I say talk to a user, they're not usually like, they don't have sort of the blinders that I have where it's like, I'm thinking about a pipeline, right? They've got like 4 or 5 storage systems and message buses, and they're using Beam to write pipelines that connect to them, but often there's like 3 Beam pipelines. So the question is like, when I've got data and I ingest it, let's say over Kafka, go through a Beam pipeline, it writes us to a couple places, there's a couple other pipelines, and you end up putting it in like, some of it goes into data warehouse in one format, some of it goes into Iceberg in another, and then they're like, well, it's kind of too high latency, so like, but like, where is the latency going, right? Or when the data is getting dropped somewhere in the middle, they're like, I think that there's like a problem here where I'm filtering in a way that's not what I want. And so increasingly focusing on the app level instead of like within the pipeline level, I think is an important direction for Beam's future. Boop.
Thanks. So I'm going to talk about the last pillar here, which is responding to kind of the moment here, and that is first-class machine learning support within Beam. You might say, like, we've already got that to some degree, and I think it kind of traverses the existing pieces and our future direction. We do have really excellent model serving support within Beam already, and that's the place I'm going to start here. So we want to enable both real-time and bulk inference workloads, and that includes running things locally, running things remotely, smoothly. One future direction and place we're investing is making it easier to run remote inference in a way that doesn't overwhelm whatever system you're using and allows Beam to provide feedback to the runner so it doesn't outscale whatever you're talking to. But in general, we want to make it really efficient and easy to apply whatever model you want in the middle of your pipeline. So There's, I think, future tech here. There's also just expanding to meet whatever needs arise as there are new frameworks that come up. Like I talked about Vayyala yesterday, there's going to be plenty of more frameworks to come. We want to continue to support those well and make sure that Beam can kind of thrive with the new demands of the ecosystem. The next piece of this that I'm going to talk about is feature generation. So again, this is a place where Beam is already extensively used. People use Beam to take input data from various sources and create features. But I think there's, right now, kind of this missing gap of working really, really well with feature stores that are out there. I also think this feeds into some of what Ken was talking about of providing higher level turnkey transforms. Right now we've got the building blocks, and those are great for building features, but it would be great to have kind of higher level library support. And again, just working really well with the ecosystem. We have our enrichment transform, which allows you to go and enrich data from various sources, and we want to expand support for kind of a variety of feature stores. Similarly, along the enrichment path, we want to make it really easy to enrich with embeddings and just support the whole embedding lifecycle. So embeddings are kind of a core part of working with large language models. I think there's a lot of use cases for using Beam to both generate embeddings that can then be used for semantic search or RAG or other applications. And there's also a lot of potential opportunities for enriching existing data with embeddings from vector DBs. If you want to do bulk queries against LLMs especially to support the RAG process. Right now, Beam has kind of growing embedding transform ecosystem, both with ML Transform, which supports generating embeddings and, again, enrichment. But I think there's, again, just this gap of broader ecosystem support. We want to make it really easy to kind of keep your whole embedding workflow within Beam. So that includes writing to your vector databases, that includes enriching from your vector databases, generating embeddings across multimodal data. Right now, we've got really good tech support, and we're working on more support there. I think this is another area that is just kind of rapidly evolving. So a theme here is kind of keeping up with the ecosystem as it moves forward and trying to stay ahead and lead in this space as well. Another space where there's a lot of opportunity is anomaly detection. I think there have been a few talks about anomaly detection or adjacent topics here. But this is an area where Beam can really shine, especially for kind of streaming online use cases. Beam is really well positioned to do this, and we've started to put together primitives here, but I think there's a lot of room for people to come in and collaborate and make this even better. And then the last thing I'll call out is new capabilities. And this slide also got messed up. But the main thing here is there's a lot of parts of the ML ecosystem that Beam is well suited for, but doesn't necessarily touch. And there's parts of the ecosystem that Beam is not well suited for today, but could be in the future. So things like providing higher level transforms for model evaluation, you can already do this really well in Beam. Things like offline training and supporting kind of distributed training, it's something that Beam could do, but we don't have support for it yet because it requires iteration and there's work to be done there. But I think there's opportunity for us to provide this kind of broader ecosystem support eventually, whether that's iterative or online. And then I think like the biggest thing here is that, again, this is just a really fast-moving space. And so we want to be both proactive in leading in the space, but also reactive to whatever cool new technologies come next. To wrap up, so here are kind of the three pillars that we called out. But I've said this is a vision for Beam. And I think that that's a really important thing to call out here is like, this is kind of where Ken and I think things are going based off of what we've seen from other people and where we think there's opportunity for Beam to grow. But the most important part of Beam 3.0 is going to be the community. And everything here is built on top of you all and the broader community. So kind of the call to action here is get engaged with this. There's a lot of opportunity to shape what this vision looks like. There's a lot of opportunity to add new pillars or contribute to some of these work streams as well. But I think, as with all open source, if you don't have community, you're not going to really have a usable thing. So I'd ask everybody if they have ideas to jump in. So where will you take Beam 3? Thanks.
Okay, thank you so much, Danny and Kenneth. As I mentioned, that was a pre-recorded talk from the in-person event that we had in New York City on July 8th and 9th, where they shared a bit of the roadmap of where Beam has been going. I mean, what has happened with Beam lately and where it's heading. So exciting times. We posted in the YouTube, in the chat, a link to the slides. Sorry about the messages. We're just we tried to put several messages, but YouTube chat filters any messages with a URL. So sorry if those messages confused you. So we are about to do our last talk of this mini online event, and we have Rajesh Vayyala with us. Rajesh was scheduled to present at the in-person event, but he had an issue. He couldn't travel, but he's here with us. Thank you so much for making the time, Rajesh. Let me add you to the stage. There we go. And let's please, okay, there we go. Yes, we can hear you, Rajesh. Hello, how are you?
I'm good, Pedro. How are you doing today?
Awesome. Thank you for taking the time to do this. I know that you're with a very tight schedule. Thank you for joining us for this. So you will be talking about building seamless data ecosystems, a real-world integration with Beam, Kafka, and Iceberg. Thank you so much. The floor is yours. I believe we can see your slides there. Yes, we can see your screen. So the floor is yours, Rajesh. Thank you.
Okay. Hi, everyone. Good morning, good afternoon, and good evening across the world. So the topic that I would be presenting today is build seamless data ecosystems and real-time or real-world integrations with Apache Beam, Kafka, and Iceberg. Again, welcome everyone to Beam Summit 2025. As Pat mentioned, I was not able to join the live event, but I heard that the event went great. So thank you for all the attendees and the organizers. So I'm here excited to share how Apache Beam, Kafka, and Iceberg can work together to power scalable, resilient, and real-time data ecosystems. So as we see, the data grows in complexity and volume. Integrating the right tools becomes essential for delivering business value efficiently. So again, my name is Rajesh Vayyala. Before we get into the technical content, I would like to briefly introduce myself. I'm a principal data architect at a global data query company where I'm leading the cloud data warehouse modernization. I have 10 years plus of experience across finance, marketing, logistics, and non-profit organizations. I'm specialized in enterprise data modeling and governance, building cloud native data platforms to support reporting, analytics, and now machine learning and AI requirements. Other than work, I'm active contributor in industry forums, editorial boards, and technical conferences. I'm passionate about data architecture, business strategy, and real world projects to help nonprofit organizations. And today I'm here to talk about the real world architecture patterns and key lessons that are essential for building resilient, future ready data platforms. And I also had an opportunity to present about best practices for schema evaluation in Apache Iceberg at the Apache Iceberg 2025, which is happening in April. So if you'd like to go through the presentation, you can check check the YouTube channel for Apache Iceberg, and you will be able to look at the presentation. So let's get started. I have a quick agenda here. I would like to talk about some of the pain points in fragmented data environments. Then I will introduce the three technologies and how they work together. Then we will dive into like a couple of use cases and how we can implement some of the patterns, architecture patterns, and takeaways you can apply in your own projects. So why seamless data ecosystems? As data comes from everywhere, whether it's applications, APIs, sensors, third-party providers, the teams often build separate pipelines for batch and streaming, which creates maintenance nightmares. So seamless ecosystems solve this by bringing everything into a cohesive architecture that supports real-time, governed access to trustworthy data. So these three technologies each solve critical problems in modern data landscape. First, let's talk about Apache Beam, which serves as the processing backbone. It unifies batch and stream workloads, allowing you to write once and run anywhere. It supports stateful processing, windowing, and current and custom transformations. And then Apache Kafka, which acts as the ingestion engine. It handles real-time streaming with strong ordering, replayability, and massive scalability. It decouples producers and consumers to improve flexibility. And the last one, which is Apache Iceberg, that provides the foundation for reliable, scalable analytics. It brings a data warehouse-like features such as asset compliance, and then schema evaluation and time travel to the data lake. Together, these technologies enable modular, open, and scalable ecosystems, whereas the Kafka handles the ingestion, the Beam handles the transformation and unification of data, and Iceberg makes it ready for governed analytics. So this is a reference architecture that represents the core pipeline, whereas the Kafka ingests events from multiple systems, and the Beam acts as a processing engine that cleanses, transforms, and enriches the data. And the final output lands in Iceberg, where it is stored in a scalable asset-compliant format for downstream consumption. So this design supports portability, modularity, and real-time performance. So here is a open source Apache data stack reference data architecture that I picked up from the internet. So this diagram, it illustrates a complete ecosystem using tools like Apache, Nifi, Kafka, Hive, Delta Lake, and HBase. And on the left, we have a variety of data sources like IoT, databases, files, apps, all funneled through Nifi for enrichment and routing. And the Kafka handles like high throughput streaming and ensures reliable delivery to data lakes and warehouses, whereas the data is stored in Delta Lake, backed by HDFS, and governed using Apache Atlas and Ranger. And we have compute engines like Spark, Airflow, and On manage the processing and scheduling. And then the output flow into visualization tools like Grafana and Superset or analytical platforms like Mahout. So this visual shows how open source Apache tools work together to build a cohesive, secure, and scalable data platform. So the key takeaway is your stack doesn't need to be monolithic. Modular tools like Beam, Kafka, and Iceberg integrate well into these architectures. There are common integration patterns in real-time data processing. So the first one is point-to-point, which is simple but limited in flexibility. And then we have pub and PubSub, which enables multiple consumers to independently process the same Kafka topic. And then we have the Lambda pattern, which combines batch and streaming pipelines for accuracy and low latency. And then we have a Kappa pattern, which removes the batch layer entirely by reprocessing from Kafka. So though the Spark is the focus here, Apache Beam supports similar patterns and offers more portability. And understanding these different patterns helps us to design the right pipeline based on latency, durability, and maintainability needs. So here is a common architecture patterns when working with Apache Beam, Spark, and Iceberg. So these patterns give us the flexibility to build both real-time and batch data ecosystems, depending on the business need. So the first one is stream to lakehouse, where we use Beam, which is like Beam to Iceberg. So this is a real-time pattern where Apache Beam reads streaming data, typically from Kafka or PubSub, transforms it, and writes directly into the Iceberg tables. Because Iceberg is ACID compliant, it allows us to safely append streaming data, enabling real-time dashboards or anomaly detection pipelines. So this is perfect for low latency data use cases. And the second one is batch only ETL. So this is a classic nightly batch ETL pattern where Spark creates large volumes of historical data, process it in bulk, and writes it to Iceberg. So this is ideal for cost efficient operations or handling large data sets that does not require immediate freshness. So this is often used for daily reporting or ML model trainings. And then we have the hybrid pattern, where many companies combine these days the Beam and Spark, whereas Beam handles the real-time ingestion, while Spark performs periodic batch jobs like backfills, deduplication, or compaction. So this gives the best of both worlds: up-to-date streaming data and robust historical completeness. So this pattern is common in e-commerce or finance environments. And then we have the open source. So in this open lakehouse. So in this pattern, where Iceberg is treated as a universal table format, accessible from multiple engines, whereas the Beam or Spark writes the data, and Iceberg exposes it through catalogs like Hive, Metastore, or REST. So this allows query engine like Trino, Presto, or Athena to access the same data without duplication. And this is great for like open and interoperable data architectures. And we have the CDC, which is a change data capture. So here we use some CDC tools to capture changes from OLTP systems into Kafka, whereas the Beam consumes those CDC events and writes them into Iceberg with full historical context. So this enables like audit trails, time travel analytics, and real-time reporting for transactional systems. So the last one is the compaction via Spark, which is also like the optimization. So even when using Beam for ingestion, Spark often plays a supporting role for optimizing Iceberg tables. So it can rewrite small files, compact partitions, and improve query performance downstream. So this pattern ensures your analytical workloads remain fast and efficient over time. So these patterns are modular and composable. We can start simple, say with Spark plus Iceberg, and evolve into real-time Beam-based pipelines as we mature in the process. So the important thing here is that Iceberg sits at the center as the unified storage layer, supporting both streaming and batch seamlessly. So here I have a couple of use cases. I don't want to mention the company names, but at a high level. So on the left, you can see there is an example where a financial institution, a bank, streams customer transactions via Kafka, and the Beam consumes the data, applies anomaly detection using sliding windows, and enriches with customer metadata. So the results are written to Iceberg and used in fraud monitoring dashboards. So this ensures both real-time responsiveness and historical traceability. And on the right, where you can see a manufacturing company where thousands of IoT devices produce events every second, and Kafka handles the ingestion, and Beam standardizes the formats and units and adds metadata and writes that cleans data to the storage, which is our Iceberg. and partitioning by device and time enables the fast queries and ML training at scale. So here is a quick slide about unlocking analytics with a lake house. So the legacy data warehouses were designed for batch loads and static reporting, but today's organizations demand both real-time insights and scalable historical analysis. So that's where the lakehouse architecture shines. By integrating Kafka for ingestion, Spark for processing, and Iceberg for storage, you get a lakehouse that supports fast queries, handles schema evolution, and allows both streaming and batch use cases. So this enables analytical teams to build dashboards, train ML models, or run ad hoc queries on fresh and historical data, all from a single source of truth. So the result is like lower complexity, higher agility, and better business decisions. If you'd like to break down the picture or the architecture pipeline on the right hand side. So in the first, where you can see there is a API layer that is doing the file uploads, like the raw JSON files to S3, or Minio, and then the raw files lands in the landing zone, which is like unprocessed and stored securely. And then there is the event streaming with Kafka, where each upload triggers a Kafka message with a pointer to the file location, keeps Kafka lightweight, and decouples storage from processing. And then we have the processing layer, which is a Spark, where Spark structured streaming consumes Kafka messages and then retrieves files from Mio, then cleans and validates and writes to the Iceberg tables. So this enables near real-time data transformation. And then where we have the storage layer, which is like the Iceberg and Nisi, where Iceberg ensures asset compliance, schema evolution, and time travel, whereas Nisi adds Git-like versioning, branching, and reproducibility. And the last we have which is a query layer, where there is a Trino. So Trino queries the Iceberg tables directly with high performance, and it also supports SQL joins and dashboard integration with BI tools like Tableau. A few proven industry best practices is always enforce like schemas to avoid inconsistencies, and then break pipelines into modular steps, like make them easier to test and reuse, and use Beam's built-in metrics and Kafka monitoring tools like Prometheus or Confluent Control Center for visibility into pipeline health. As these tools are growing rapidly, the Beam now supports SQL and many more connectors. And Kafka has tiered storage on powerful streaming in processing, like via KSQL DB, and Iceberg is adding like support for branching and RESTful catalogs. All three are backed by the vibrant communities that are solving real world problems, in the open source innovation nowadays. So the conclusion and the future outlook is, so if you're modernizing your data platform, this stack gives you open source flexibility, cloud native scale, and real-time responsiveness. So the big message is that in the modern data ecosystem, where you need to be like open, modular, and scalable, Apache Beam offers the flexibility to bridge batch and streaming, whereas Kafka provides robust decoupled streaming pipelines, and Iceberg gives you a powerful data layer that supports everything from SQL queries to machine learning. So looking ahead, the ecosystem is evolving fast. Expect stronger lakehouse patterns, better catalog interoperability across engines, and more innovations driven by the open source community. So I'd like to thank you all for attending this session. I hope this gave you both the architectural grounding and practical inspiration to take your data platform to the next level. So, feel free to reach out if you have any questions, and also feel free to connect via LinkedIn.
Actually, let me, yeah. Hi, Rajesh. Yes, I wanted to show you the slides with your LinkedIn. So that's the best way to reach out to you, right?
Yes,
LinkedIn will post that in the, well, I don't know if we can post in the chat. I believe a moderator needs to post that in the chat. Thank you so much for joining us, Rajesh. Let me just wait a bit to see if we have any questions from the audience watching. Um, your slides, when you get a chance, please share them with us so we can
okay,
publish them on the website with a recording of this talk and
sure.
in the Apache Beam YouTube channel. We know that, as I mentioned, that you have a very tight schedule. Thank you for making the time for joining and sharing with us.
Mhm.
Because yeah, we did want to have the content of this talk, and it was unfortunate that you didn't get a chance to present it in the New York City event. But thank you for joining here. Um, we're posting the LinkedIn, your LinkedIn contact, in case anybody wants to reach to you later with any question or anything. Because I don't think I'm not seeing anything on the YouTube chat for questions. Thank you so much, Rajesh.
Thank you.
Have a good rest of the day. And thank you, everybody, for joining us. This was the last talk of this mini online event. And we will be publishing the recordings from this and on the other talks from the in-person event in the Apache Beam YouTube channel within the next couple of weeks. Thank you, Rajesh. Thank you,
Yep, thank
everybody.
you,
Have a
Rajesh.
good rest of the day. Bye
Thank you.
bye.
Bye.